Here's a sample conjugate acid-base pair type of problem. It says identify the conjugate acid-base pairs in the reaction between ammonia and hydrofluoric acid in aqueous solution. Notice the aqueous written there. Well, let's take a look. One way to do this is just to memorize these, Ammonia is a common base, so it's going to be a Bronsted base. This is going to be your Bronsted acid, hydrofluoric acid. And the base will always make a conjugate acid, Ca+. This is a conjugate base, Cb-, so that's what we have. Bronsted base, Bronsted acid, conjugate base. How to identify each? You can memorize it or by what they did. What did NH3 do? It accepted a proton. That's what acids do. What did HF do? It gave up a proton. That's what Bronsted bases do. Now let's identify the acid and base pairs for water reacting with water. I like the fact that this is mechanistically shown here. If you go on to take organic chemistry, they love these arrows to show exactly what happens because it gives you such a nice detailed view of what the reaction is. Water has an electron-rich component. They call that a nucleophile in organic chemistry. No, you don't have to know that. But those lone pairs of electrons are ready to attack. This is a male-oriented view of the world. So this attacks that weak electropositive part of water. If this is negative, those are positive. This is a potentially acidic proton, they say. When it does so, you have an excess of electrons, so these simply go over to oxygen, giving you H3O+ and OH-. I just can't resist saying something like this without explaining the mechanism. Notice it's a reversible process. And in fact, it doesn't happen much at all. It's highly reversible. So what's going on? Well, this water molecule must be acting as it's accepting a proton, so it's acting as an acid. It's accepting a proton, therefore it's acting as a base, my bad. And this is giving up its protons. That's what Bronsted acids do. And so we have that forms the Ca+ and the Cb-, the conjugate acid, and the conjugate base.